You've probably heard of wavelength division multiplexing, or short WDM, as a technology to combine multiple optical signals onto a fiber. But have you heard of optical circulators? And if so, do you know how they work? If you want to find out more, stick around and we'll check it out. WDM uses different wavelengths to combine and separate the individual signals. But an optical circulator does the same thing using the same wavelength. So how does that work? Well, the easiest way to understand how it works is to actually retrace the signals going through the optical circulator. So let's start off with the signal coming in to port number 1. And the first thing that will happen is it will pass through a so-called beam displacer. And what a beam displacer basically does, it will separate that signal into its different polarization states, and it will do it horizontally. So the next stage is then to pass through so-called Faraday rotators. And what those Faraday rotators do is they rotate the polarization of the signal. But the important part here is that this one will rotate it by plus 45 degrees, whereas this one will rotate it by minus 45 degrees. And the result is that we will then have two signal components that both have the same polarization state. Now, since they have the same state, they will pass through this next beam displacer unchanged. But then, once again, we've got a set of Faraday rotators, meaning that after that, we will have the two different polarization states again, and then it will pass through the beam displacer. But in this case, it will actually go through it in reverse. So in other words, instead of separating the different polarization states, it will actually combine it, meaning we will have our output signal on port number 2. So that's the one direction. Now let's have a look at the other direction. So we've got a signal coming in here, and like I say, this is using the same wavelength. And it will pass through this beam displacer, so in other words, it will be separated into its different polarization states horizontally. Now, it will go through the Faraday rotators, and after that, once again, we've got the two components that have got the same polarization state. But now here, this is where the actual clever part of the optical circulators happen. And that is due to two reasons. You can see we've got this beam displacer here, and we've got the signal, the brown signal coming from port 1 going to port 2, as well as the other signal going in both directions. And that's the same here. But the point is that these signals going back and forth always have the same polarization state. Whereas the signals coming here, they actually have the opposite polarization state of that actual port, meaning that these two signals will be displaced, so they'll be redirected. And here's the second clever part of this, and that is that this beam displacer is actually rotated by 90 degrees. And that means that these two signals being displaced or redirected, that won't happen horizontally, but instead vertically. So in other words, these two signals now will go down onto this new path. And since we're then once again passing through these Faraday rotators, we will then have this signal, the two components and the polarization states returned, and then going reverse through the beam displacer, meaning that those two will be combined. And there we go, that's our signal coming from port number 2, going out on port number 3 using the same wavelength. So what is the main use case of a optical circulator? Well, the most commonly known one is an OTDR measurement, because what an OTDR does, it sends a signal onto a fiber, and then it needs to measure the reflection of that signal. And obviously that reflection will have the same wavelength, but since it's going through this optical circulator, the reflected signal will come out on a different port, so the OTDR will be able to measure it. But of course, that's only one of the possible applications. So, I hope you learned something today and that you enjoyed this video. If so, please leave a comment. And of course, follow our channel so that you get your regular dose of brain snack. Until next time, bye-bye!